For today's program, I will start by speaking a bit about the technology itself, what are the applications, and what are the main building blocks that we needed to work on. Then I will address what are the challenges that we still have open, especially technical challenges that we still have to deal with. And of course, open the door to new paths. What can we bring new to this area? Then this will be the state of the art. Then I will introduce a bit of our work and suggestions into designing tunable sensors, focusing into strategies, how to change linearity and of course then sensitivity, and then how to locally change the reference orientation that allows us to detect multiple vectorial components of the magnetic field. In the end, again, I will bring everything together and talk a little bit about some perspectives from my personal point of view for this field. So let's kick off. In terms of magneto-resistive sensors, so the main idea that we need to bear in mind is that these are thin film multi-layer devices. They are built by stacking different materials. And their main property is that once we approach an external magnetic field, we can see a change in the resistance measured in these different stackings. And because we engineer these materials to have either a fixed magnetization orientation or one that can change with the external magnetic field, we can definitely tag along the different changes of the resistance once we expose the systems to such a magnetic field that we want to detect. So this is the basic. There are different types of magnetoresistive sensors. There are actually a myriad of types of magnetic sensors. I will also show you a bit of that. But today I will mostly choose to focus on two main systems that I have worked with and I have now been working with for some time. These are the all-metallic giant magnetoresistive stacks and the tunnel magnetoresistive. And all of this has a purpose because if one is able to convert a signal, whatever their nature, into a magnetic field, we can then find a way to measure it. And current applications of this magnetoresistive sensor, the X stands for giant, stands for tunnel, stands for anisotropic. It can also stand for whole, but not in this presentation in particular. But the applications of these sensors are definitely infinite. So nowadays they are quite pushed by the automotive industry. So you can think about detecting the position of the wheel, detecting, for example, not only in high power lines, but also in the batteries of electrical cars, how much electrical current is passing through when you are charging or when electricity is flowing by. You can also think about in a factory setting or even in an automated robotic hand that you need to precisely know where your robot is picking up your packages or is placing something. So you can think about high precision position sensors. And of course, if all of us want to go travel either inside the building or outside, many times we need to know where we are. So we can also think about the use of these magnetic sensors to help us navigate through different environments. So these are some examples and snippets of general applications, but also we can move then towards the more biomedical and biological field. And here also magnetoresistive devices, they find a lot of different applications. So you can think about using them to help place new prosthetic limbs, detect biomagnetic fields from our body, help quantify different biological tests, as for example, lateral flow immunoassays, or use them as a matrix to quantify DNA or other bioentities. So these are some possible uses for these sensors. And of course, we go a bit back to the main building block. And as I said, in this main building block, what is important to keep in mind is that we have different nanometric layers. And, in order to develop each one of those applications that I just talked, we need to take into account what materials are used, what materials do we need to use, and of course, why do we need all of them? And for that, I divided these main building blocks into what I call 4 main parts. I will speak briefly about the role and the importance in each one of them to devise a really competitive state-of-the-art sensor. I will first start by the spacer. So indeed, the spacer defines in a simple view which type of sensor we are going to build. In this case, I have chosen here an all-metallic giant magneto-resistive device. Typically, I have used these packings with current flying or current in the plane. If you go a bit back, and if you look into seminal works, you should definitely take a sneak peek to the seminal works of Albert Schacht and Peter Grunberg, awarded the Nobel Prize in Physics in 2007 for the discovery of this independent scattering mechanism in multi-layer thin films. In their case, it was with current perpendicular to plane, but today you can see many applications where such systems are very similar, and we can have two different states of the relative orientations of the magnetization, one with low resistance and one with high resistance, and here in between is where we want to detect the magnet. So this is when we have a metallic spacer. We can then move to state-of-the-art tunnel magnetoresistive devices, where instead of having such a metallic spacer like copper, you now have an oxide. State-of-the-art nowadays is with MGO, very thin MGO barriers, and of course the electrodes, the ferromagnetic electrodes. You cannot see one without the other. And in this case, the current now flows perpendicular to plane so that electrons can funnel through the barrier and experience independent tunneling. If you want to know more about this and the mechanisms of this phenomenon, you should definitely take a look to also very seminal works by Yuasa, where coherent and incoherent tunneling is discussed, disordered barriers, and also how can we use them nowadays, even still to develop new applications and new uses for these devices. So this brings us in a very simple picture to the key role of the spacer layer. So in setting what type of magnetoresistive device are we going to design, a all metallic, one with a tunnel barrier, but the truth is neither one of these materials can be seen without the ferromagnetic electrodes, being it the sensing layer and also the reference layer. And here we can use different types of ferromagnets. Typically, they are cobalt-based alloys. And one of the key properties that we need to ensure for such self-standing, self-biased devices is that we can indeed build a linear response within a narrow window of field. And this is the key point of also the technologies that I want to share with you, is that we can start by deposition to have two different orientations of the magnetization, parallel in the low state, anti-parallel in the high state, and the transition between these two states is done via a square curve. So you just quickly switch, mostly via a domain wall, the status of the magnetization of one of the layers. Then, for particular applications, and if we all think about sensors, we always need to measure one quantity relative to other quantity. In this case, we are going to measure magnetic field, and we are going to measure in truth the change that such an external magnetic field induces in one of the key layers, and how this layer changes relative to the other ferromagnetic layer. So we have to inbuild the reference, and because we have this inbuilt reference in the stack, we can then shape it to obtain this linear behavior. Again, in a simple picture, the most important part of this is all done at the sensing layers. Of course, there are multiple strategies to obtain this linear behavior. These strategies that I'm showing here, they are quite well established, they are mature, and several of them are used in commercial devices nowadays. So just for you to have an idea. Yes. Now it responds. So shape anisotropy is quite widespread. So we just shape the device into a very narrow stripe, and with that we can locally change and tune the magnetic anisotropy at the sensing layer. And with that, we are able to again change the tilting of the curve, so the slope of the linear curve, just by modifying the geometrical size of this device. And as you can see, this is a nice way of tuning the sensitivity, coming back to the tuning part. However, if one thinks about how the slope is changing, we are indeed being able to detect larger fields in this case, but the sensitivity of our device to detecting such fields is clearly decreasing. So indeed, we can gain in terms of how much field we detect, but we are losing in terms of sensitivity. It works for many users, but maybe we can do better. And if you think about really going small, and when going small using this strategy, we are losing the sensitivity, then we can, of course, use a different way. Like, for example, instead of having a simple sensing layer, we can softly thin it, so increasing its anisotropy so that it stays in plane for a longer time. And this is a good strategy that we have used to linearize very, very small devices. Because if you want to have a very highly resolved mapping of the field, for these particular magnetoresistive sensors, it does change, or it does depend on their size. So we need to ensure that even for these small sizes, we have a linear behavior. But as always, being able to linearize, even at such a small scale, comes at a cost. And one of the key points is using this strategy, which may seem quite nice and flexible at first, is that we have quite an increase in the noise level at the sensing layer. And I'm already putting here another keyword, which is noise. Noise is definitely a key parameter to take into account in these devices, because we can design an ideally beautiful linear device that can detect a large range of field, but we also need to be able to solve or to resolve the minimum field that we can really detect in the final application. So sensitivity, detectivity, minimum detectable field, they are all coming together, and in the end all go to the materials. So these are just some ideas, but recently, to kind of tackle this problem, a solution was proposed that instead of using these quasi-single domain like structures, like the ones I showed before, we can now move and think about using a vortex domain state at the sensing layer. And in this case, we move from quite thin ferromagnets now to quite thick ferromagnets. so that the magnetization can itself give rise to this vortex state into the free layer. And then we can profit from the middle part of the magnetization versus field curve of this free layer, where it is purely linear. What we need to take into account is what is the nucleation and the annihilation field for this vortex, because this will set the linear operation range for such devices. And it was also shown that indeed we can have this beautiful linear dependence in a clear window of field. So interestingly enough, these vortex-based sensors show a lower intrinsic noise level. So this solves part of the problem of going very small and have increasing noise for linearization. Now we see here a different approach, where even going small, we can still gain some advantage in terms of noise. Of course, we are losing in terms of sensitivity, but it's always a trade-off and always depends on what application you are targeting at. So this was a quick overview on the types of materials that we can have on the sensing layer, but more than the types of materials, what do we need to do with them? So the standard stacks nowadays, they use nickel iron and cobalt iron for metallic giant magnetoresistant devices, and cobalt iron boron based electrodes for MGO, because to have the coherent tunneling, they need to have a particular crystallographic structure. So for now, this is where the most or the best devices are. And these are some limitations that we can clearly identify how to merge, how to trade off sensitivity, linearity, and noise. But finally, I move to the bottom part of the stack. And in this case, the reference layer. So the part of the stack that we use to have a set magnetization so that we can always judge what the field, external field is related to. Unfortunately, we cannot look into the reference without talking a bit more about what comes underneath it. Because in terms of structural, crystallographic structure, roughness, etc., this play a big role in the full behavior of the stack. So just as a quick overview for these magnetoresistive devices, the reference includes, of course, the buffer, an exchanged bias bilayer, and most of the times also a synthetic antiferromagnet, both of them to provide good stability, good thermal stability, good immunity to cross fields, so that we can really use it without worrying about losing our reference. And one of the, let's say, still open challenges that we can find nowadays in these stacks is, of course, how to push further their operations at high temperatures. And we can think about how the different buffers do influence the growth of the stack. We can think about designing experiments with very simple bilayers, but the truth is that we cannot see this full stack only one block by one block. And in a recent work by Pedro, he clearly showed how could we interlink this magnetic behavior of a simple change bias bilayer and directly connected it to a full state-of-the-art MTJ stack, and how can we infer from one to the other which behavior to expect, and also why the differences, why so many differences. Of course, we have to take into account interdiffusion, intermixing of all these layers when we are talking about complexities. From the shaft point of view, most of the standard shafts do use ruthenium as spacer, but if we really want to push their operation to high temperatures, there are some very interesting works that consider different materials, such as iridium, as the interface, and the temperatures that these drugs can survive are quite competitive, even up to 400 degrees. So this builds the overall picture of the building blocks for these materials. I already gave a couple of hints on some of the challenges that we are facing. Of course, starting always from the material side, and this links quite well to this middle point of the presentation. So linking what has been done to what we can do. So from these building blocks, we can discuss a bit what are the open challenges in terms of how to push further the limits of performance of these devices. And indeed, we are always looking for more sensitivity. So if we can resolve ever decreasing fields, we can, of course, develop really precise and highly resolved metrology tools, in this case for magnetic field. So there are a lot of works that you can check out. For example, how to use these Euler alloys to provide a higher signal in MTJs. So another critical point, and if one thinks about application, this can be one of the main issues that we really need to ensure that works well in these devices, is to have low noise levels. There are different strategies that we can use. We can use external fields to stabilize the domains. We can use internal fields to make sure that the fluctuations of the magnetization are small. We can also think about more in terms of design, spec, in the vertical, the multiple stack specking, the arrays of sensors. These have been shown to decrease significantly to increase the detectivity. And also consider different materials such as cobalt, iron, boron, tantalum, cobalt, iron, boron, silicon for the free layer. Then have larger temperature working windows of temperature. So different antiferromagnets are being considered nowadays. So manganese nitride, manganese nickel, and also different interlayer materials. So these are just a couple. We can also think about hybrid technology integration, for example, mixing superconductors with magnetoresistive sensors, or even microelectromechanical systems. So all of these bring certain advantages to this technology. And of course, regarding the noise level, I would like to point out that there's going to be a nice presentation later on this AtC-AtG by Mahmoud Hasli, exactly on this. Then we know which challenges we need to tackle to push the limits, but we can think ahead. We can think about, okay, what can we bring new? What do we need to devise so that we can keep this technology competitive? As highlights, I would like to bring the tunable sensitivity. It would be ideal to change the sensitivity on demand. This would definitely widen the possibilities. Here is just an example for vortex sensors. Also add function, so devices with multifunctionality. This very recent work by the colleagues at INL show a mixture of a MEM-resistive and a magnetic sensor device, which is quite interesting. Then, of course, being able to detect 3D fields in one element. These would definitely reduce the errors when mapping the vectorial nature of the magnetic field that we have around. So for final devices, being able to monolithically define different orientations would bring quite some interesting applications. And of course, devise new materials and new applications. And for that, I would like to call your attention for all the several presentations that come next to this one still in this session. Of course, as a disclaimer, not only XMR sensors exist, there are magnetic sensors in the flux family with quite high sensitivity. We can never forget the Hall sensors, which are dominant in the commercial applications. And also, we can not ignore the up-and-coming optical-based techniques with the nitrogen vacancy centered in diamond or the optical pumping magnetometry, which have also huge sensitivity capabilities. And again, I would like to point out to the presentation that is going to take place in one of these techniques. We can never forget these competing technologies because we needed to ensure that even our magnetoresistive sensors are pushed into the future and that we keep them up to date and competitive enough so that we can still find a market for them. And for that, I'm now going to go through few suggestions that we are putting forward on how to design these tunable sensors. So the first one will be focused on changing linearity and because of that, the sensitivity. And for this, so this work is being done by Pedro Araújo in collaboration with the team in Lisbon. And what Pedro has been exploring is how, starting from the channel magnetoresistive sensors, how can we locally in the free layer induce changes using artificial defects, and with that control how the magnetization behaves, and especially control the local anisotropy barriers. And if you think about with this strategy, we can decrease the local anisotropy field critical for linearization, but we may also be able to induce different axes different easy axes on the sensing layer. So in that sense, we could also think about multi-axiality in a single element. And by using this strategy, right now, the first step is, of course, to being able to design a stack that can bear these local anisotropy modifications. And of course, that helps us to detect them. So for this case, TMR junction with a very thin free layer is considered. And then a very challenging part comes into how to embed these small nanoholes into the free layer without destroying this barrier. So this is quite a technological achievement that Pedro was able to show. And also, in the end, when measuring these devices, the first thing that we notice is, although we start in this case from almost a linear curve, but with very low magnetoresistance, because again, we have a very thin free layer, so we are in the super paramagnetic limit. Once we start to embed these local artificial defects, we see that the linear part is changing, and in this particular case, and surprisingly, the magnetoresistive signal is also changing to our favor. So overall, we see an increase in sensitivity with the change of side or the pitch of these holes, despite very low magnetoresisting signal. So what Pedro is figuring it out now is why. Why do we see this change in magnetoresistance? How can we use it in our favor? Is it because we have local stray fields that do help to better orientate the relative magnetization of the free layer to the reference layer? In the end, how can we use this to our favor? So just as a critical point, then in the end, he was able to show that you can indeed use these defects to locally modify the anisotropy. We can see that we can tune the linear range. We have some changes in sensitivity. We can still not do this on demand, but we hope to get there. Of course, we have to pay a price. The fabrication is a bit more complex and there is some increase in coercive field, but nevertheless, we can embed these structures we can change their geometry and dimensions, we can definitely change its sensitivity and possibly embed different sensing directions. So the final tunability point that I would like to talk about is an exploratory route on how to change the reference layer orientation. So here I have to bring the person that is doing the work, that is Floris. And Floris has started with this quite exploratory topic and the question, can we, starting from or taking some inspiration in the laser repinning strategy that is used nowadays to locally define different orientations in whetstone bridges just by shooting a laser pulse, hitting and then cooling under a magnetic field, similar to magnetic annealing. So can we start from this idea, maybe get some inspiration for quite some recent works where the free layer of magnetic tunnel junctions was switched using ultra-fast laser light. And well, can we apply that to the reference layer of magnetic sensors and think about how can we locally reverse its orientation, which will then be the first step into detecting multiple components of the external magnetic field. So here in the group at TU Eindhoven, in particular Bert Koopmans and Reinhold Hofeisen, they are specialists in this all-optical switching of multi-layers. So the phenomena of pure all-optical switching was discovered in the ferromagnetic systems some time ago. And in the group, we use multi-layers of, for example, cobalt gadolinium to address and to find and tune applications for these systems. So this is the inspiration. We use the optically active layers as a means to switch the magnetization, and we build them near our antiferromagnet. So we can flip the laser and then drive the reversal, and our exchange bias will fall. As a side note and a bit of publicity, if you want to know more about this and the expertise of Bert, I would definitely point you to different channels that IEEE Magnetic has available. You can see here in these two channels, videos from all distinguished lectures are available, and some others from the schools of magnetism from IEEE. So definitely use them as a good resource. So going back now to the work of Floris, so the first step is to demonstrate that we are able to do that, and we start from a simple out-of-plane perpendicularly magnetized stack, embedding the optically active layer and the exchange bias bilayer, and its first results are quite promising. So after shooting the laser, we are able to see that the exchange bias switches to the other side, at least you see the change in value. And depending if we use a field to help or not, these changes are more notorious. So another interesting feature is that you can go back and forth. So you can keep recovering the previous state, the previous first state after submitting it to the laser light. And interesting enough, we can also see how the resilience of these materials changes with time when we keep, for example, increasing the power of the light that we are putting in. So if you want to know more, if you want to learn about the mechanisms behind it, I would definitely invite you to, if you are at NMM in Dallas in November, please go and talk to Floris about this work. So I will just wrap up here the final two slides with the summary and my perspectives. So in terms of summary, I try today to give you an overview of the field applications, current untackled challenges. I showed you two vias where we are definitely trying to push these new paths into magneto-resistive sensors. So both in tuning sensitivity and linear range, and in refining the reference layer. And finally, for your thoughts, I would like to do a bit of marketing, because this area is still an area that has a lot to be done in terms of devising new sensing strategies, new materials and devices. Think about how we can improve the designs, how we can profit from integration with different technologies, and in the end, how we can think about the systems of sensors that we need to use and to make them into final commercially viable products. And last but definitely not least, one never works alone, and I do have to thank all the members of the team in both Eindhoven and also in Lisbon, and our collaborators in the University of Oviedo. And I know I went a bit over time, but thank you so much for you being here and listening to me.
Thank you, Diana, for the nice talk. So there is already a question in the chat from Sonal, and asking, could you please give some insights on optical control vortex samples for magnetic sensors?
Some insight, well, I can give some insights depending on what you are looking for. So the first thing that is important to take into account when designing these multi-layers for to accommodate vortexes is, of course, what are the materials that we use in the free layer and their thickness. Typically here, if I remember well, I think they are mostly nickel iron based. Also the shape. So you need to ensure that you pattern a round shape to be able to accommodate the vortex. And also another quite important trick in these devices is that when defining the free layer, we need to ensure that we also stop very well at the barrier or the spacer to define this quite circular area into the free layer part. And of course, depending on the trade-off between your dimensions, geometrical dimensions of the pillar, the thickness of your free layer, the intrinsic anisotropy of your free layer, you can then embed a vortex. But you have to have all of these parameters just right. Otherwise, you may end up with a C-shaped structure or not such a well-defined vortexes. I hope I addressed some of the insights.
Thank you very much. There is another question from Giovanni Masciocchi. So please.
Hi. Thanks for a very nice talk. I really liked it. I have a question about what you said, that when we have weak pinning, then we can increase the noise level. I think it was slide 12.
It's actually the other way around, but yes.
Yeah, so why in this specific case you have this increase of noise, like 1/f noise? I think it was the previous slide. Yeah, here. So
this one.
Yes. So yeah. Why do you see that?
Yes. So our findings showed us that at the interface, because here in this weakly pin, the sensing layer is no longer a single ferromagnet. So we have the ferromagnet, nickel iron, for example, interfaced with the manganese iridium. So we have an antiferromagnet for these weakly pin layers. So in the end, they are exchange bias at the sensing layer. And locally, the fluctuations of the magnetization of the free layer when you are in the linear part will increase significantly. That's what we have seen. That's what we have seen reported from previous work from Coe's group also, that whenever you measure the noise, if you think about a full magnetoresistive sensor, if you measure the noise at the sensing layer and at the pinned layer, the pinned layer noise, the magnetic noise from the pinned layer is always higher. And it's the same that we see here, because typically we have more local inhomogeneities due to exchange bias, and this increases the magnetic noise component to the full noise spectra of the sensor. And notice also here that we focused a lot in the low frequency part, because we were targeting bio applications, so mapping slow time dependent applications. The word is missing me. And in this case, the 1/f noise is dominant, and of course the component of the 1/f noise magnetic type will be even higher.
Okay.
So long story short, local fluctuations of the magnetization at the free layer are quite significant.
And you had higher noise in the presence of cobalt iron on top of nickel iron, or vice versa?
We always no, in this specific case, we didn't see much difference with that, with these two stacks, because it was dominated by whatever was happening at the interface.
Okay, thank you. Thanks a lot.
Looking forward to your presentation also.
Thanks.
Okay, thank you very much. There is another question in the chat, but I guess we have to move on. So we can you can continue the discussion in Gather Town.